So for the sake of people watching at home, a request was made to bump active 6 to Thursday. It is now bumped to Thursday, and we fixed the attempts. So you should be up to like 20 attempts. Is it set to lose points per attempt?
No.
Okay, which is fine. So unsaturated. When we talk through our alkenes, or for all of these kind of reactions, there's multiple things that we have to deal with. So one is what we're talking about is our alkene can act as a nucleophile, reacts out with our acids and our electrophiles. So all of that should have been fun. The other thing that we can address is that we get cis versus trans. This double bond in particular is shown as trans because our groups are on opposite sides of that double bond. Okay. The last kind of content thing that comes out of this is this concept of unsaturated and saturated. This applies to more than just alkenes. It applies to alkynes and carbonyls and any kind of pi bond, and ultimately also rings as well. What we're talking about with saturated and unsaturated is that if I look at a carbon chain, let's just pick a 4-carbon structure, this saturation is saying that is kind of in reference to, it's not kind of, it is in reference to the amount of hydrogens on the molecule. So if I look at this particular molecule, I have fully saturated it with all the possible hydrogens I could put onto it. Okay? Even if I go through and replace one of those with, say, an oxygen and then a hydrogen, it's now still fully saturated. We've maximized all of our possible slots with hydrogens. Okay? When we talk about unsaturation, what we're saying is we have removed hydrogens. So if I remove a hydrogen from this molecule, I have this point, okay, this, I don't know how I want to show that, okay, but this hole, if you will, where it has lost hydrogens, it is now unsaturated. Okay? This should naturally cause kind of problems popping up within our thought processes because that carbon is now missing its octet. So if we're going to look at a molecule that has now become unsaturated by losing a hydrogen, we've got issues within the structure, and it's now a reactive structure. We're looking at crazy intermediates and things like that. So we still want something that is stable that has lost hydrogen. And it turns out the way that we do that is we can't just lose one hydrogen, we have to lose 2. Right? And if I do that, you'd be like, well, but aren't both of those carbons now missing their octets? Yes, and it's fixed by adding a double bond or adding a pi bond. Okay? So this molecule is now a neutral structure. Okay? All of our octets are satisfied. But it is unsaturated. I replaced hydrogens with a pi bond instead of a sigma bond. And that's really all that it's referencing. Okay? That pi bond can be carbon-carbon. It could also be carbon-oxygen. So this particular molecule has now been unsaturated twice. Whoops. I just removed one hydrogen. I have to remove the other one. Okay? Has now been unsaturated twice. So you can hear people referencing how much unsaturation a molecule has. So they can say it was singly unsaturated or doubly unsaturated. Okay? You'll also hear reference sometimes to degrees of unsaturation. Those degrees are referencing how many times, how many sets of hydrogen were removed from the molecule.
So it'd be like 2 sets, like would be 4?
So 2 sets would be 4 hydrogens were removed if we had 2 degrees of unsaturation. Okay? You can also hear it referenced, which is kind of a new term to me within the last probably 6 years, an index of hydrogen deficiency, because somebody decided that unsaturation wasn't a cool enough term and they needed a bunch of fancier keywords within it. Okay? And that's ultimately referring to the same thing. How have you removed hydrogen from the molecule? Okay? We set it up in a system where it has less hydrogen than it could theoretically achieve. Okay? As you go through and change the identity of certain elements, the kind of calculation of how many hydrogens are possible to saturate or unsaturate can also change, and it can turn into some complex formulas. We don't care about the complex formulas. All I really want you to be able to do is say, yes, that molecule is saturated or unsaturated. And that's it. So if you're seeing all sigma bonds, it's saturated. If you're seeing double bonds, it's unsaturated. Right? If you see multiple double bonds, it's multiply unsaturated. Okay? Where I believe we ended, what is today? Today's Thursday. Where we ended Tuesday, we talked about our saturated and unsaturated fats. Okay? What they're referencing is the presence of double bonds in the fat molecule itself. Okay? And it turns out our saturated and unsaturated fats also come from different animal, or not animal, it's the word I'm thinking, living organisms. So our plants produce unsaturated fats, and our animals produce saturated fats. Okay, so most people, oh, saturated fats are bad for you because they're coming from, not really. Okay, but that's why margarine came into existence. We say, well, saturated fats are bad, so we'll use plant fats that are unsaturated, but then because they're unsaturated, they break up how the structure packs. Why is that important? If I look at a molecule, okay, a fat, ballpark, where all of those structures are saturated, these now pack really nicely against each other. And I can take another one and put it up next to it. What happens if they stack really neatly against each other? They turn into a solid. We get really strong intermolecular forces between them because they can stack neatly. So we get solids. Okay? That's why plant or animal fats are bad, because they turn into solids in our bloodstream. Not really, but again, that's kind of the argument. If we look at, or the initial argument that was made, if we look at plants, what happens is they introduce these double bonds. Those double bonds can create kinks within the structure. And if there's kinks within it, this structure is going to have to bend away from it, and now it can't stack quite as nicely. And if it can't stack quite as nicely, you don't get the same strength intermolecular forces, and now everything weakens, which is why they turn into liquids. So a margarine comes along and says, well, plant fats are better, but we want them to be a solid so we can spread them. Like I like my butter to spread. Okay, I don't want to pour oil all over my bread. Okay, so what do? We go through and we take our unsaturated fats and we convert them into saturated fats. How? We add hydrogen. Okay, we add H2 across the pi bond. Okay, what does that do? It takes our healthy fat and now makes it saturated. Well, now it's clearly still healthy because it came from a plant, not an animal, and now we can market it as this great healthy alternative to butter because it's made from plants. Doesn't really work like that. Okay, they've since changed their marketing scheme and say it's healthier because it's more sustainable from plants as opposed to animals. Okay, but that's kind of the history of how we look at those processes, and a lot of that just comes from how we learn about what those different things are. Okay, and how people understand them. Kind of makes sense? So for the sake of this question, really all you're being asked is which one of those has a double bond? B. There you go. Make sense? I think there were a couple of them. Do you think you get it enough where you think you could answer all the other ones, or should we go and find the other ones?
Is hydrogenation the same?
What is hydrogenation? This was supposed to be written in a way that was legible so that you could see it. Sort of. Close to that. Okay? But if we look at the breakdown on this, we're looking at hydrogen, as in what are we adding? Hydrogenation is adding two hydrogen atoms. So if I take an alkene, it's usually easiest just to show that one, what I'm doing is taking that hydrogen molecule and I'm reacting it so that I now have the hydrogen added across the double bond. The process of doing that is hydrogenation. Okay? Not to be confused with hydration. what the heck's hydration? Hydration is referencing, as you might expect, if you were dehydrated, it's because you hadn't drunk enough water. Hydration is the addition of H and OH, aka water, across the pi bond. Okay. I always got those confused, for the record, which is also why I don't like the English language, because they sound too similar, but that's my own problem. Okay, so just be kind of aware of that. It's one of the reasons why when you look at your exams, you tend to see a whole lot more structures than words, because I get less confused by structures, whereas other people, I think, get less confused by words. And so I try to walk the balance between providing both words and structures so that you can understand what's going on with it, depending on which point of view you align with. Not perfect in that, but I try. Make sense?
Can we go over 10? Because I don't know.
So no, there's definitely a couple, right? So now we're talking about increasing reactivity to hydrogenation, okay? So this is now a whole nother level. Hydrogenation is the process of adding hydrogen, but this is now asking about reactivity. Okay, so what we're saying is how does this react with hydrogen? Well, in the course of this reaction, we have to get our alkene close enough to the hydrogens so that it can form those bonds. Okay? So it's largely a proximity argument. If we moved or changed the reaction to, say, HCl, our conversation changes. Why does the conversation change? Because the mechanism changes. When we look at HCl, what we end up forming is a carbocation. So in the case of HCl, that reaction is really dependent on that product. When we go through and look at the hydrogenation, since it's happening in one fell swoop, simultaneously we get different dynamics with these. Right? Since the question asked about hydrogenation, let's look at hydrogenation first. Okay? I want the hydrogen to directly interact with the pi bond as easily as possible on top. What would prevent the hydrogen from reacting?
Other bonds.
Other bonds. So if I go through and look at these structures, what I should be able to see is that structure 1 is di-substituted, structure 2 is mono-substituted, structure 3 is tetra-substituted. Okay? So as you phrased it, structure 3 has more bonds. What is that going to do?
Not allow the hydrogen to get in there.
Make it more difficult for the hydrogen to react. So that should reduce its reactivity. So 3 should be the slowest. 1 should be the next, 2 should be the fastest, because it's most accessible. Right? When we go through and look at the other reaction with HCl, the dynamic changes, because now it's not all happening at once. I'm concerned about making this carbocation, which means which of my pi bonds is going to react the fastest? 3, because it makes me the most stable carbocation. So the reactivity will flop on us depending on the dynamics of that individual reaction. Kind of makes sense?
So when the question asks hydrogenation, we're just saying H2.
Hydrogenation is just H2. Okay? It's slightly more complex than that. I don't think I gave you a video that actually showed that, but when we look at hydrogenation, this should look kind of similar. Come on, pen. Okay. We saw the bromine reaction, right? Okay, and we ran the bromine reaction. This went this way, that left, and then these electrons came down, and we formed that 3-membered ring. Okay, it's still happening all at once, but we're getting a slightly different mechanism. Why? Why would bromine form that 3-membered ring, but hydrogen just goes whoop? That's one of the big points. Bromine is significantly larger than our hydrogen. That bromine being large enough can coordinate to both carbons simultaneously. Hydrogen is small. It can't bridge that gap to be able to do that. So that's one explanation. The other explanation is when we look at Br2, that bromine, the other bromine, is a great leaving group. Is the other hydrogen a great leaving group? No. Right? So bromine being large allows for the facilitation of these electron motions. Hydrogen does not allow for this well. Right? Hydrogen actually doesn't allow for it so well, doesn't react. What's the word? I want to say the negative. Hydrogen doesn't react at all? Because saying well doesn't make sense. Maybe it does. Hydrogen doesn't react well with our pi bond. So what we have to do is add something into it to help it interact. So if you look at the reagents, when we talk about the hydrogen reactions, we have H2 and platinum or palladium. Okay? Those platinum and palladiums are really just a solid surface. Okay? They're metals, so they allow the passage of electrons. What we're talking about reacting is our p orbitals. So what happens? The p orbitals coordinate to the surface of the metal. Hydrogen coordinates to the surface of the metal, and the hydrogen can then coordinate or kind of trade its electrons through platinum into the bottom of our pi system, creating that bond. So the platinum has to facilitate the electron transfer for our hydrogen. Hydrogen can't do it on its own. Right? Bromine being large can facilitate all those electron motions on their own. Kind of, sort of? Okay. Does that answer all those questions?
One more.
Generate more?
One more. What's the best reagent to use when you're going for an alkene, but not an alkyne, but not an alkene? It's question 12.
So if we're moving through here, we're again talking about hydrogenation. So we're talking about the addition of hydrogen, and there were multiple reagents we could use for this. Okay? Assuming H2 at the top of all of these, we could do H2 and platinum or palladium. Whoops. We can do H2 and palladium with barium sulfate. We can do H2 and palladium with the word Lindlar's catalyst, sometimes written after it. And then at some point, this NaNH3 showed up, okay, in our list. Oh, and it's not on that, so we'll come back to that. Right? So there's a bunch of ways that we can add hydrogen across a pi bond. Okay? If we're looking at hydrogen with just the metal, what does it react with? All pi bonds. There is zero selectivity. So what it will do is react with alkenes and alkynes. There's no bars hold, it just runs the course. Okay? If I want it to slow down and not do that, I have to add something to it. I have to add something to it to prevent it from doing that extra chemistry. Right? Well, what happens in the next one? Palladium and barium sulfate. What did I do? I added something. What does the barium sulfate do? It does something different than what happened up here, which means that prevents it from reacting with something. Right? Lindlar's catalyst. I've added another word. Why did I add another word? Because it's preventing it from reacting with something. Right? This last one, extra goofy, and we'll come back to that one in a second, because I think I'm going to remove that one. Okay? Isn't in our list, so we don't have to worry about it. So what does that mean? We go through and look at our list. H2 and palladium/carbon. It's just hydrogen and our catalyst. H2, that's hydrogen and our catalyst. Hydrogen and nickel, okay, another metal. Heat and pressure, okay? We're just saying we're forcing that in. H2 Lindlar's, ooh, we're adding something weird. Right? This is that adding of something weird that's now going to do something different. What's that something different? It's that it's targeting a different functional group. Right? So when we're looking at our conditions that hydrogenate alkynes but not alkenes, what we're trying to do is find that thing that causes a shift off. Okay? Something that doesn't fit that pattern. H2, those first two, We're just adding the hydrogen and a metal. Hydrogen and a metal. Hydrogen and what the hell is that? Hydrogen and what the hell is that? Okay? Those should set up some massive kind of red flags that those are now targeting something specifically, whereas the rest, we're just adding hydrogen. Kind of, sort of? All right. Within that context, we are then going to encounter some other issues. First and foremost, I didn't proof this well enough. They threw in Crabtree's catalyst. One of the things that's obnoxious within OChem is that it's an evolving field. And guess what we do within the evolving field? We create more chemicals. As we create more chemicals, what should we do with those more chemicals that we have created? We should name them. Cool, we can name them. Does that mean every student coming through needs to know what it is? No, and I would argue that most students should not know what it is. Crabtree's catalyst is now looking at a secondary specialized reagent. Why do we need to talk about it? I honestly don't know. Right? Active clearly thought it was important enough to include. I should have checked this enough to say, don't do that. Okay? In this case, I believe the one that we're fishing for is Lindlar's, and I will straight up say I've never heard of Crabtree's catalyst. Not even on my radar. And of course, I'm going to run into batteries all over the place. Okay? Theoretically, what active would do would then be, and see Lindlar's. Lindlar's is, I think, in our list. And I could be wrong on that, but I think that's on the list of chemicals.
I've seen it before somewhere.
Okay. I think it's in our list, and for that reason. Okay? It's used specifically to react with alkynes, not alkenes. Okay? Ideally, what they would have gone through and done here is provided this list underneath of saying what all the other ones did, so you at least learned that. Otherwise, you're like, well, is Crabtree's a random reagent? Was that just made up? I don't know. I've never heard of it. Okay? Kind of, sort of?
Yeah.
So to that end, I fully apologize. Shouldn't have seen Crabtree's. Lindlar's was on the list of things that you should recognize. Okay, what are we talking about for that list? Sorry for the scrolling. Right there. So for this particular question, what I would expect you to do is be going, and for, I would argue, all of the actives, is go back to these summary lists. Because these summary lists are now providing all the reactions that I think you should know. You should be using these to kind of work your way through it. Okay? And if we go through and look, what happens with the Lindlar catalyst? The only thing I'm showing it react with is the alkyne. When we look at just the alkene, nickel, H2 and platinum or palladium, I'm not seeing Lindlar's catalyst up there. Why not? Because it doesn't react with alkenes. Is there another piece of evidence to suggest it doesn't react with alkenes? What happens when I react the alkyne with that catalyst?
Shows an alkene.
It makes an alkene. If this reagent reacted with alkenes, would I get an alkene at the end of that reaction? No, because it would have continued to react. Okay? So there's implied information behind that, and that is dangerous, but we have to be kind of aware of that. Okay? I did say I would double back to this sodium and ammonia one. I'm really on the fence on it because it's an important distinction between these two. But I think the primary focus for this course should be maximizing your understanding for the common reactivities, finding your positives and negatives. This is not an easy one to find positives and negatives on, and if we go through and look at that reaction, what are we doing here?
Making
a trans alkene by doing what? What changed to go from the alkyne to this alkene? You added 2 hydrogens. Do you obviously see 2 hydrogens within those reagents?
No.
That's because it's not easy to see. It's a crazy mechanism. It's really neat and beautiful and all that fun stuff, but that's way beyond the scope of what I feel this class should be. So I'm really trying to not ask questions about that. It may very well show up in the active, because when I built active, I thought of including it. I'm going to try and remove that from the exam material. Make sense? Okay. To exam material, I want to point out a couple things. Number one, again, these big review things. So scroll through and find these slides, because these slides are important. If we're going to actually number them, 2, 3, sorry, I'm going to scroll. 28, 29 might actually be it. 44 and 45. Okay, those are the major ones. There are a couple reactions that come up in the play pause it videos that I think you should still be responsible for. Actually, the acetals are on this one. Are they? Yeah, the acetals are on this one. Okay. There is, I thought there was one that wasn't. This one, our BH4 and lithium aluminum hydride. Those reagents aren't listed for these functional groups. You don't see those reagents listed there for those starting materials. So you should be aware of those. They aren't in a reaction summary. Okay? Kind of makes sense? But those reaction summaries you should have at hand as you're moving through active and as you're moving through practice assignments. To that end, to Shay's request, I did the old review and Electrophile edition. I managed to go through and start generating a document that covers the unit 1, which you didn't have like a summary of a whole bunch. Here's a whole bunch of questions to practice. So I went through and created a whole bunch of questions. You can see how much whole bunch because it's taking a while to load. Okay. That has a whole bunch of the unit 1 stuff, and this particular one covers Electrophile edition. So the most recent stuff we just talked about. Okay. I didn't feel I had enough time to get through the Nucleophile edition stuff, which we'll be talking about today and next week and probably EAS. Okay. So hopefully I'll have that put together later today and I can get that up there also. But this provides practice. How much practice? I think you're hitting 100 questions. Okay. So there's lots of questions within it. It's 100 questions, so let's go ahead and just throw it out there. For the previous exams, what I did was pull these kind of questions from my ability to, and I started weeding things out. So I said, oh, I want to ask this for an exam. I'll leave this for them to do homework on. I'm going to do this for an exam, and started kind of going back and forth creating 2 documents. I have not done that. As in, the vast majority of your questions are questions that you will have already had access to see either within the review documents or the old exams themselves. Make sense? Okay. I can still modify, change, answer, randomize stuff, but the final, you're pretty much seeing all the questions that you could possibly see. Okay? Other last second questions? I kind of want to move on. No? Okay. With our Electrophile edition, I think we're as far as I wanted to get. Remember, we deleted some things, or I erased some things off this slide that I don't want you to worry about. If you see questions on an exam that you're like, I never saw this before, just flag it, let me know. But I think we're done with our Electrophile editions. Okay, which means we move into our Nucleophile editions, which are now shifting the chemistry from a non-polar pi bond to a polar pi bond. Okay? To be polar, need to update software. Okay? Usually what we're going to center on is our carbonyl. So we've got a carbon bonded to oxygen. It doesn't have to be oxygen, it could also be nitrogen. Theoretically, it could be sulfur or phosphorus, but those are outside the realm of what we decided were our elements for this course. So really all we're concerned about is oxygen and nitrogen, and the primary focus is going to be on oxygen. Okay? So when you look at the carbonyl, what chemistry do you see? What does that mean?
There's a partial charge.
Ooh. Okay, because it's a polar pi bond, hopefully we do see a charge differential. Different from an alkene, where an alkene didn't have a polarity associated with it, the electrons were immediately active as a nucleophile for our alkene. Our carbonyl is a little bit different. These electrons in that pi bond may be higher energy, but they're already being drawn to one side of our molecule. Okay? that can be shown through our resonance. So if we now look at our resonance, negative charge on our oxygen, positive charge on our carbon, what chemistry do we now see? What about that charge? How would that charge react? So when we're thinking what chemistry, acid, base, nucleophile, electrophile. Right? We see the electrons up on our oxygen, so we might go through and call that a nucleophile. Ah, there we go. Or a base. We go through and we see the positive charge on our carbon, so we might go through and call that an electrophile. Or, I'm being obnoxious, can I call that an acid? For it to be an acid, what does the positive atom need to be? It needs to be a hydrogen. Is that carbon a hydrogen? No. So when we're looking at our carbonyl, these are our three primary categories for our reactivity. We don't have the acid chemistry, at least explicit. We'll come back to it in a second. We've got the electrophile chemistry of our carbon. We have the nucleophile or base characteristics coming from our oxygen. Okay? Those should be our very first primary categories of, yes, this is now our primary focus. Okay? So let's push on it a little bit more. Would I expect both the negative and positive to be equally likely to react? This goes all the way back to the very first unit when we draw out Lewis structures. Why? Couldn't I just say that the carbon is more likely to react because it wants to accept electrons? Yeah. Okay. So I'm going to make the argument that your explanation doesn't hold water. It doesn't allow me to differentiate.
The negative is more likely to react to the
So if it's not the negative, it's got to be the positive. Because I'm yelling about the negative. So the positive has to be more likely to react. Why? Say that? Octet. There it is. Okay? The carbon is missing an octet. The oxygen has its octet. Okay? Octet is our primary number one thing that we need to deal with when we're dealing with Lewis structure. That carbon is what drives the reactivity. So when we talk about our polar pi bond chemistry, almost universally it centers on the electrophile. Okay? Which means, what do I need to find to react with it? A nucleophile. So it's now just looking at all of the reagents and saying which of those reagents give me a negative. If it gives me a negative, I would expect that negative to react at that carbon. Ta-da, there we go. Okay? That will necessarily generate some issues because as we satisfy that carbon's octet, we then see that the oxygen is charged and we now need to fix the oxygen. Okay? So our number one reactivity would be our electrophile. And kind of, what is the phrase, a number one with a bullet? I don't understand what that meant, but I think I've heard that before. Okay? Our electrophile chemistry is sitting at our carbon. We now go back and look at nucleophile base for our oxygen. Okay? Which of those is more likely? Okay? Something about size. It's going to boil down to the difference between nucleophiles and bases. What do nucleophiles react with? Okay.
The inside of the structure.
The inside of the structure is probably the better answer. So nucleophiles have to get inside the molecule, whereas bases just have to be on the outside. Which one's easier? Bases, because they're acting on the outside. If we consider this nucleophile and we look down at this carbon, what's out here? Could change, but more than likely we're looking at a larger extended structure, which means we have some steric hindrance, which means nucleophile is less likely. So if we're going to predict our chemistries through here, our primary focus is the electrophile of the carbon. We're then seeing the base characteristics of the oxygen, and then maybe we could drill out to the nucleophile characteristics of that oxygen. Okay? as far as you're concerned, the oxygen is actually not nucleophilic. Okay? It is a very rare reaction to see the oxygen come through and act as a nucleophile. It does happen, okay? But it's super, super rare. Okay? These are the big, broad strokes that I want you to be able to get. I want you to be able to look at a functional group and tell me these kind of reactivities. Make sense? Okay? So, full disclosure, I guarantee on the exam, I'll give you a picture of a functional group with the list of acid-base, electrophile, nucleophile, and say which of these apply. You need to be able to say which of them apply. When we look at a carbonyl, what ones are we going to reference?
The carbon into the carbon right
Our
along.
electrophile characteristics and our base characteristics. We should not be selecting nucleophiles, and we should not be explicitly dropping acids. Okay? And this is where the explicitly dropping acids come, that sounds weird, dropping acids comes into play. Let's push a little bit on our structure, because this structure is very generically drawn. We don't know what's out here. So I want to add a little bit more information. I'm now going to say I have a carbon out here and a hydrogen. Is this going to change our conversation a little bit? Yes, it is. How does it change our conversation?
It changes what could react with the
Potentially.
stereochemicals.
When we talked through our chemistry behind this, we said our carbonyl was primarily electrophilic. Secondarily, we had the oxygen acting as a base. And now what we've done is we've stepped one atom kind of further away, or potentially two atoms further away from the primary functional group, our carbonyl. What we want to see is, does that introduce more chemistry? Okay. One thing that should scream, I asked, what could that positive carbon act as? And we said electrophile right away, and I said, could it act as an acid? Should we also say acid? And you were like, oh yeah. And then we said, why not? There's no hydrogen. I've now drawn a hydrogen. Should I be concerned about acidity? Okay. And we should actually get a mix of answers here. Right? Because if we just draw out what we've talked about as far as our carbon-hydrogen bond, that carbon-hydrogen bond is nonpolar, which means if I were to try and go through and remove that hydrogen and make H+, I'd be generating a negative carbon. Can carbon stabilize that negative charge very well? No, which means what about the likelihood of having that molecule act as an acid? It won't. It's highly unlikely to act as an acid because the atom holding that charge cannot stabilize it. Right? Well, isn't this that nonpolar covalent bond? Yeah. So we might go through and say, well, based off of that knowledge, we would say it's not reactive. How acidic is that hydrogen? More acidic than what? Than the CH, okay. We'd be forming a negative charge on that oxygen, right? Oxygen's at least more electronegative, so it could stabilize it. Okay, so that seems reasonable. What functional group do I call that? An alcohol, cool. What if I do this? You should know the name for this one. This is a really important one, particularly for everybody dealing with any kind of medical background, which I believe everybody is trying to do. Carboxylic acid. Has the acidity changed? Yeah, I'm going from an alcohol to calling it a straight up acid. Note, it's still HOC. Why is it now so much more acidic? that I change the name to call it an acid? Resonance stabilization of that conjugate base. The electrons can resonate inwards. I've brought another functional group near my alcohol. Those two functional groups interact in a way that is synergistic or dyssynergistic, depending on how you want to look at it, okay, that significantly alters the chemistry. When we look here, we're looking at a carbon-hydrogen alkane bond. That shouldn't be acidic, except what did I bring it near? I brought it near a carbonyl. Does that carbonyl affect the ability to remove that hydrogen? How? If I remove that hydrogen, I build a negative charge on that carbon. Can carbon stabilize that negative charge? No, but what could it do? It could resonate inwards to create a double bond. If I go through and look at the net result from that, what happens? When I remove that hydrogen, I'm looking at a negative charge not on a carbon, but on oxygen. Could the oxygen stabilize that negative charge like the alcohol? Yeah, it could. So it turns out that that hydrogen does carry some acidity. Right? So we have to be careful to not just look at the functional group, but always take a step further out to see, do I get another or kind of a compounding effect with my functional groups? Kind of, sort of? Does that suck? Depends. I would argue that's pretty cool. I don't want to be tested on it, but that's pretty cool. Okay? We're looking at how those compounding things can affect outwards. Okay? Well, what happens if I move even further away? What if I put a carbon out here? Well, that carbon's still going to have hydrogens. Is that one acidic?
No,
Why not?
they can't do the resonance.
If we removed that charge and tried to put that there, we'd have to be able to resonate inwards. We don't have that ability to resonate inwards. We have to be right next to that positive charge. That's what drove the chemistry. Kind of makes sense? Okay, so we do at least see a limit here. Okay, here's the functional group, and then I can look immediately next to it and say, there's another functional group. How do they interact? If I move one further away, I'm now too far away, and I don't have to worry about it. Kind of, sort of? Okay. Okay. So, as we kind of push on this, what ends up happening, right, is that we would then theoretically move through all the different nucleophiles that could go through and react. And our primary focus is on nucleophiles, because when we look at the carbonyl, what did we say the chemistry was? It was an electrophile. So I want to look at all the possible negatives I could throw at it. Okay? So we get strong nucleophiles. H-. Can we form H- easily? No, it's incredibly hard to form. But there are a few ways we can do it. That's our borohydride and aluminum hydride. The names kind of, or the symbols kind of hint at it. We'll also not encounter diball, so we can ignore that one. Don't worry about that one. Okay? We could look at negative carbons. Carbon is again something that's not able to stabilize charge well. How poorly does it stabilize charge? So poorly that when we generate negative carbons, it gets named after the person that discovered them. Okay? So this gets called a Grignard reagent. Okay? And I'm going to delete the acetylides as well. Okay? Because what we've generated is a negative carbon. That's so incredibly powerful and reactive that Grignard got to name the reaction and say, when you use this or when you create this species, we have to call it Grignards. Okay? Where is it going to react? At the carbon. Okay? Positives and negatives. We can then move into our weak nucleophiles, and this is probably the more relevant one. Okay? Again, based off of people's backgrounds, we'll look at oxygen, we'll look at nitrogen briefly, and we can talk about our carbon This is that acidic hydrogen thing. Enolates, we'll look at that one a little bit briefly. The hydrides and the Grignards are usually just straightforward. Find the negative carbon, find the negative hydrogen, attach it. That's the end result. Okay? That's what they do, period. Okay? Why do we care about the weak nucleophile? Or why do we care less about the strong ones? Okay? To a certain extent, they're quote-unquote easy. Okay? But to another extent, there's a big reason we don't look at them. Hydrides are incredibly reactive. What happens if you ingested a hydride? You're dead. Okay, so that's not so great. Well, what are you trying to study? Medical things. And in the medical things you're trying to study, are you trying to make things dead? No. I hope. Okay? You're trying to make things live, which means all of this chemistry of our hydrides and our carbons, Grignards and all of that might be nice and straightforward and easy because it's just negative attack the positive. None of that is particularly relevant for you because none of that is going to happen inside a human body or an animal body. Okay? Because those things are just dangerous, and really, if they did, it's death. Okay? What you would care about would be the things that keep things alive. Okay? And if we talk through most biochemical pathways within the human body, nutrition, food, biological systems, you're looking at oxygen reacting with carbonyls, you're looking at nitrogen reacting with carbonyls, and you're looking at these enolates reacting with carbonyls. And it's those reactions that biology takes advantage of. Because they're weak, we can catalyze and we can push that chemistry around so that it does what we want in very particular scenarios. These things may do what we want, but they also do what we don't want everywhere else. Okay? And that becomes the problem with the strong nucleophiles. Kind of, sort of? Okay. Okay, so I want to touch on these summary slides. Okay. Again, we've got the big summary slides floating out here, and we'll try and take a somewhat not careful eraser to a lot of these. Okay. We've got our Grignard sitting there. We've got the aluminum hydride and the borohydride. These were our strong nucleophiles up top. Up here we have the acetylide. That's a triple bond with a negative charge. That's one that kind of floats in your area that we could deal with. I think it's reasonable to just delete that and not worry about it. And then this whole kind of bottom section is also a little bit, it's probably relevant-ish, but I don't want to push on it too much, again, just because of context. Okay? So really, when we're talking about our strong nucleophiles, we've got three reactions we want to address. We've got our carbonyl, which has resonance with the positive charge. Now, how does it react with each of these individual things? Okay? So let's take a look at that first example, our borohydride. Okay? Officially, sodium borohydride. Formulas are pretty meaningless. What we need to do is to be able to convert that formula relatively quickly into a Lewis structure. But because we did Unit 1, we're able to do that fast, right? Metal, sodium positive, because it's a metal, what could we do? We could ignore it, because our metals really don't do anything. Which then leaves us with our boron with 4 hydrogens around it. If we went through and looked at now formal charge on that, we would note that the boron carries a negative charge. Okay? This is an interesting one to note. If we think through most of the time, when I draw a negative charge, what do we typically see on that oxygen? Lone pairs. And officially, we should be drawing those on there. That's valid. Does the boron have those lone pairs? Nope. Okay? So when we consider the reactivity, our charge is sitting very squarely on that boron as a negative charge, but it has no lone pairs. Why is that important? If it doesn't have lone pairs, can it act as a nucleophile? No. That's really flippin' weird. We have a negative atom, And we think nucleophiles, we think negative. I have a negative atom, and yet it can't act as a nucleophile. And a lot of that has to do with the chemistry of the boron itself. If we go through and look at boron, it has 3 valence electrons, which means when I look at a happy neutral boron, that's what I get. What's the hybridization of that blue boron? sp2. What's left over? A p orbital. How many electrons are in that p orbital? 0. There are no electrons in that p orbital for that blue boron. How did it become the red boron with a negative charge? Where did it get the electrons from? The hydrogen. What's happening is we're taking H minus, that coordinates to the boron, thereby giving us our BH4. So when we look at sodium borohydride, the reactive species there isn't boron, it's hydride. Hydride can't stabilize the charge. Exactly right. It can't stabilize the charge. That's why it has to coordinate to boron to stabilize it for it. Okay? There's only certain elements that can pull off this chemistry because we need that empty orbital so that I can drop the hydride in there. Boron is one of those elements. What's the other element? Aluminum. How do you know aluminum is one of those other elements? Okay, there's 2 answers. One, we look at the periodic table, the element immediately underneath boron is aluminum. They have the exact same electron configuration. They have the exact same ability to stabilize these negative charges. That's pretty cool. How else do you know aluminum? It's actually up on this board. That's the other reagent. Instead of borohydride, we have aluminum hydride for the exact same reasons. Right? How else do we know the hydrogen is the negative one? This one is much, much harder. We could look at the difference in electronegativity between the boron and the hydrogen. And if you look at the periodic table, you'd be like, but boron's closer to fluorine, shouldn't it be more electronegative? You're right, that's the trend. That's not the answer. And if we look up the difference in electronegativity between boron and hydrogen, hydrogen actually has a higher electronegativity than boron. Which means when I look at these individual bonds, the electrons are spending their time on hydrogens, not the borons. So BH4 supplies H minus. How many H minuses does it supply? 4. Each of those hydrogens is still more electronegative than the boron. Okay? So BH4 can reduce, or sorry, that's a bad term to use, can add H minus to a carbonyl. So I could use one of these to reduce or add hydrogen to 4 of my carbonyl compounds. That's pretty cool. Okay? It's not quite as simple as that because it's so reactive as a molecule. When it encounters water, say in the atmosphere, what happens? Water has a positive hydrogen. What does that positive hydrogen do to a negative hydrogen? They partner up and make H2, hydrogen gas, which then bubbles out of the solution and you could ignite. Yay, explosions. Okay? So BH4 gives us this. Okay? We could go through and do the exact same thing for our aluminum. And our aluminum hydride does the same thing. But if it does the same thing, why do I need it? Right? Let's think through our hydrogenations. How many hydrogenation reagents did we have? 1?
2.
We had several. We had 3 or 4. Why did we have 3 or 4?
Because they did different things.
They did slightly different things. One of our hydrogenation reagents only reacts with alkynes. The other one reacts with everything. One reacts with alkynes to make cis double bonds. The other one reacts to form trans double bonds. So we have different reagents that target slightly different things. Why do we have two reagents here? They do slightly different things based off their chemistry. Can we take a swing at how they are different from each other? What are you thinking? What's that? Size. Boron is smaller than the aluminum. What does that mean about the bond length? So bond length is nucleus to nucleus. If aluminum is larger, what happens to the bond length? It also gets larger. Right? If I hold $5 right next to me versus $5 out here, where is it more likely to be stolen? Out there. The longer that bond, the more reactive it becomes. What does that mean? The aluminum hydride is more reactive. How much more reactive? So reactive that if we take a look, borohydride is supplying an H plus in the exact same step. Aluminum hydride is supplying the H plus in a second step. Because if I try to do it at the same time, what happens? A vigorous reaction of H plus with H minus to produce a massive amount of hydrogen gas and a massive amount of heat. So much heat that it self-ignites and it literally explodes. We don't like that when we run chemical reactions. Okay? The sodium borohydride is stable enough that it doesn't react that quickly with our hydrogen source. And so it might produce some, but it's not enough and enough heat to self-ignite. Lithium aluminum hydride, on the other hand, will. Okay, so we want to adjust those chemistries. Well, why do we care? A lot of it comes back to the different types of carbonyl compounds. Okay? And if we think through it, are there different types of carbonyl compounds? Yeah. When we talk about a carbonyl, we just said that. Okay? If I had a carbon and a hydrogen, that's... I know. Aldehyde. If I put a carbon and a carbon, now it's the ketone. If I put a carbon, oxygen, hydrogen, carboxylic acid. If I put a carbon, oxygen, carbon, ester, nitrogen, amide, straight up chlorine, acid chloride, oxygen with another carbonyl, and anhydride. So there's a crap ton of different ways that we can modify the atom next to it to our carbonyl. That's so many different carbonyl compounds that I'm going to want to choose different reagents depending on what that structure is. Do I care that you know what those... No, don't stress about that. What I care about is that you acknowledge that there's different conditions on which you want to do them, that our lithium aluminum hydride is vastly more reactive than our borohydride. We have hints in that when we look at our reactions. Okay? We have hints at that when we look at size differences of our atom. There's one more hint. What else changes between boron and aluminum? Electronegativity. Boron's higher on the periodic table, which means it's more electronegative. If it's more electronegative, those electrons between the boron and the hydrogen are more equally shared. Here, they're less equally shared, which means the hydrogen's even more negative. This is why lithium aluminum hydride is so ridiculously reactive. Are there even more differences? That says sodium. This one says lithium. Is that different? Yeah? Does that also manifest? Yeah? Do you want to worry about it? No? Okay, let's not worry about it. We've covered enough things to differentiate those. Okay? Grignard. What's happening with the Grignard reagent? Okay? Well, Grignard went through... Okay, that's R, meaning any carbon source, and he was somehow able to make carbon bond to magnesium. Okay? I don't need you to know how that happens, but what I need you to acknowledge is that we have that bond structure. Okay? I can do any connection out that other end. Okay, that could be a triple bond, that could be a double bond, that can be a ring, any connection I want out that other end. What charge is bromide? Typically. Negative. What charge would magnesium be? Try again. You want another hint? Try again. Oh, come on, that was a good hint.
Extra negative? Extra
What? Yeah.
Oh, double positive.
Magnesium, second column, is a +2.
Ah.
What kind of bond do I have between magnesium and bromide?
It's an ionic.
It's an ionic bond, which means this isn't magnesium metal, it's magnesium ion, because that's an ionic bond. What charge is the magnesium? Positive, positive. I hate writing positive, positive, and want to write positive too, but for the sake of this thing, we'll see in a second. Bromide, because that's ionic, would be negative, right? So those two charges cancel out, which is why I don't see any charges written up there. Okay? That was kind of a weird jump on my screen. Okay? But I still have this positive, but I still don't see that positive up there. Why not?
Because carbon's negative.
If that was an ionic bond, what is this one? It's also ionic. Okay? There is one remaining positive charge on the magnesium. Where are the electrons in that bond spending all their time? On the carbon. And if carbon gains those electrons, it becomes negative. So the overall structure, when we look at it, those cancel out and we see a neutral charge. But because we have this metal here, we should be acknowledging that that metal to a non-metal is an ionic bond. The only one we really care about, or what we could do, is kind of break this down and say, well, I have carbon negative, I have magnesium +2, and I have Br minus. Of those, which one am I most concerned about? Why the carbon over the bromide? They're both negatively charged.
Because that's what wants to connect to the...
You're saying because the answer, I don't like that. Carbon can't stabilize the bromide as well. That's a slight step above because that's the answer. Do better. Why can't carbon stabilize the negative charge as well as the bromide? Electronegativity, better, but even more important, size. Why is size the one that trumps? Remember, we talked about our reactivities. We start with charge, then size, then electronegativity. So there's multiple things that contribute to why bromide stabilizes that negative charge well. Okay? There's multiple things that also contribute to why the carbon does not stabilize that negative charge well. Okay? So by all rights, we would say it does not exist. This can't happen, except in this very particular circumstance that Grignard was able to pull together, we could generate a negative carbon. Once we have that negative carbon, what do we want to react it with? A positive. And what did we just discover within our carbonyls? We have a carbocation, which then means I can take my negative carbon and react. What happens? I would get my negative oxygen, 1, 2 don't change, and I neutralize my carbon's charge. Kinda, sorta? Okay. But that's charged. Even with the hydrides, would it be charged? How do we fix the negative charge on the oxygen? What did we say was the chemistry of that negative oxygen? It was a base. What do we react with bases? Acids. So we have to follow it up with an H+. Sodium borohydride, we could get that H+ from the solvent. Okay, it's usually some kind of alcohol. For lithium aluminum hydride, we had to follow it up with H+ as a secondary step because the lithium aluminum hydride was so Blooming reactive. The Grignards, we also have to follow it up with an H+ reaction. Note the highlightation of the red all the way across. Because what we're saying is we have to run that in a secondary step. Kinda, sorta? How are we feeling? Ish? Cool. that didn't look ish. That looked like, can you stop talking? Okay, so when we talk about our strong nucleophiles, those are the ones I want you to be familiar with. I want you to be able to recognize those ionic bonds. Okay, identifying those core structural pieces are what allow you to make these leaps of predictions. Okay, that's really powerful. If you don't understand those core kind of fundamentals, what you're saying you want to do is memorize each of these reagents. Okay? I believe the way the final will be written, you can get away with doing that. That's a lot of questions to memorize. We're sitting probably in that 60, 70 question range. Okay? I think I said formally 70, right? Did I say that? Okay? That's a lot of things to memorize. Okay? So you've got to find a balance between that. Make sense? And if you're good at memorizing, then memorize away. Okay? Find that balance for you. Weak nucleophiles. Okay? I want to do some kind of rips through here. Okay? This is an interesting one because if we look immediately to the left, what do we see? It's not a weak one. Shouldn't have been on there, but it was part of the summary I've got. Okay? The cyanohydrin is a valuable one with cyanide. Okay? And it creates reagents that are very, very functional for creating or mimicking biochemical pathways. Okay? That said, it's a whole bunch of secondary chemistry that I don't think is worth us spending our time on. The Vidic is a strong one as well. So really what we're going to shift to is looking at our oxygen and our nitrogens. For the oxygen and the nitrogens, I'm actually even going to delete the Wolff-Kitchener. Okay, and we could look at these two as part of our reactivities. Those two are very biochemically important. Okay, what you're talking about are, there's a name associated with them, I believe Schiff bases. Okay, and you will see these if you take any kind of biochemistry class or potentially even nutrition class. There are, I know for sure in nutrition, there's things that you could talk about that are looking at Schiff bases because they facilitate certain chemical pathways, okay, that are very valuable to life. Okay? But what we're looking at, even through all of these, and I'm going to delete that Bear-Villiger one. Okay? What do the nitrogen and our oxygen have in common? Fair. Back to our carbonyl, what are we looking for to react with our carbonyl? A negative. What do both the oxygen and the nitrogen have in common? Close. Lone pair electrons. Those lone pair electrons could act as a nucleophile and react with our carbonyl. Okay? In the case of the nitrogen, it is more nucleophilic than the oxygen. Why is nitrogen more willing to donate electrons than the oxygen? It's less electronegative. Okay, which means when I bring nitrogen near a carbonyl, it does the same attack. The nitrogen comes in and attacks that positive. And what it's going to form is an intermediate structure where I get the oxygen and the nitrogen attached to the same carbon. Okay, so we get a carbon here. There's our 1 and our 2 with an oxygen out one end. I'm going to put an X out this end. Okay, that structure is very polarizing for our carbon. Okay, does not like that particular status because we have two electronegative elements withdrawing electrons from the carbon. It gets a little bit pissed, and if it has the opportunity, what it will do is force electrons to transition. So if we put a nitrogen here, both that oxygen and that nitrogen have extra lone pair electrons. The carbon, given the choice, will say, okay, oxygen, piss off. You can take the electrons because nitrogen will share them. What does that look like? That's now generating a double bond between the nitrogen and the carbon. So the nitrogen will do a full swap out for the oxygen. Okay? Through an extended mechanism, which the lecture videos, the play posits make you go through and look at. Okay? Nitrogen has an interesting feature, though. We could have multiple carbons on it, depending on its substitution pattern, whether it's a primary nitrogen or a secondary nitrogen. you get slightly different outputs. Okay? Why do you get slightly different outputs? Well, it has to do exactly with what we're saying. Nitrogen does a full swap out. Absolutely, 100% for the carbonyl. So we'd get this system. Even in that top case. What's the problem with the nitrogen in that top case if the nitrogen does the full swap out for the carbonyl? As in, there is something wrong with what I have just drawn.
It's positive.
That nitrogen has 4 bonds. If nitrogen has 4 bonds, it's positively charged. Nitrogen is still an electronegative element. It doesn't want to be positively charged. So what does it do? It attacks that carbon with a hydrogen next to it. What did we say that hydrogen was? Acidic. And if I take those electrons and make a double bond, I can connect those electrons up there. There's my reaction. That's how I get to this system. What's happening is that acidic hydrogen is coming into play. Why? Nitrogen doesn't want to be positive. Okay? So this system on the far left, where we had that nitrogen, becomes kind of an important intermediate structure to evaluate and consider. Okay? In the case of nitrogen, nitrogen is more willing to donate electrons, so it can eject the oxygen. But what if atom X is oxygen? Okay? Well, now it's creating a new special system. Okay? This is still a potentially reactive molecule, and depending on conditions, it can stay this molecule. So if we go through and look, we started our carbonyl, we move through, here's our intermediate, where we have the 2 oxygens connected. In this case, I have a hydrogen on one in the R group, a carbon on the other. I can continue to react this down out to this system, where those are 2 R groups. This is a very special particular reaction that becomes super important biochemically. I'm going to butcher it, but I'm going to try anyway. Does this look familiar to anybody? Chair flip, yeah, I accept chairs. Why else does it look familiar? You don't like that? Maybe let's try it this way. Nobody? Really? It's glucose. Yeah. I'm probably screwing up the top one. I think I got the chair flip one right. Okay. That's glucose. That's a carbohydrate. So when you talk in biochemistry about glucose molecules and carbohydrates and their stabilities and their reactivities and all of that stuff, really what you're talking about is how a carbonyl became 2 oxygens connected. Where's that carbon? That carbon has 1 oxygen connected to it, 2 oxygens connected to it. In this state, it's the halfway. I have an OH and an OR. That's known as a hemiacetal. But if I linked up this oxygen to another carbohydrate, okay, I could be creating a glucose chain. I could be, I could create carbohydrates, right?
Yeah.
I'm not very good with my biochem. Right? Multiple glucoses are carbohydrates. Is that right? Okay. There you go. Carbohydrates. Okay. And if we did that, what we end up moving to is an acetal. So when you talk about all of your carbohydrate chemistry, all of it is centered on this chemistry here, going from a carbonyl to an acetal. Okay. How does that happen? You're looking at either acid catalyzed or base catalyzed reactions. Okay. You have electrons on the oxygen. The electrons on the oxygen can go through an attack, breaking the pi bond, doing all of the exact same chemistry that we just did for our hydrides, for our carbons, and even for the nitrogens. None of that chemistry changes. All that changes is the identity of the element sharing the electrons. And because it generates a new special functional group that has relevance somewhere else, do we introduce these names of acetals, hemiacetal, meaning I'm halfway on the way to becoming an acetal, and straight up carbonyls. If we talk about our glucose molecules, we could see it out as the ring. You could potentially have also seen it something along these lines. I'm probably butchering this one pretty badly. Is it this? Is that glucose? Can you remember? Okay. So you can see it as the straight chain form. How do we go from the straight chain form to the ring form? We take this oxygen and it attacks the carbonyl. 1, 2, 3, 4. I screwed it up. That oxygen, 5, 6. That now creates your ring structure, your acetal form. Why do we want the ring structure and not the straight chain? It has to do with what we're trying to do. The straight chain is great so that I can chop carbons off of it and get energy. But what if I want to store that energy? That's where my carbohydrates come into play. I want to hide that chain, so I cyclize it. Then I can string a bunch of those together. What if I don't want energy, I want structure? Well, I can take those same glucose molecules and I can change how it makes the bond, and I get cellulose instead of our starchy, yummy foods, carbohydrates. And all it has to do with is how you make that different connection, which is really neat. And I apologize, I'll stop.